Also, all the viewers, in this video I'm going to explain circle theorems of grade 10. I start with the first theorem relating with the central angle and inscribed angle standing on the same arc. And theorem says here, prove that central angle is double of inscribed angle standing on same arc. Right, so this is the theorem, the first one which we have to deal with in the theorem of the circle. So first one we are going to prove, right? And for this we have to draw here one circle, is it? So let's draw it. So I'm making here one circle. Okay, and now after making circle we take one arc over here. So I'm marking here A and B. So from here to here is one arc, right, which I've taken as AB. And now this point is this center O I'm marking. Now what you do here is it on the arc AB we make here central angle AOB by joining ON OB, or drawing radius ON OB, right? So let's draw it. Okay, I've joined ONB and then joined ONA. So central angle here AOB is formed, and now on the same arc AB let's make here one inscribed angle. I'm taking here point C. Okay, let's find them also. So let's draw here CB and the line CA. So inscribed angle is also formed. So here ACB is the inscribed angle on the arc AB, and angle AOB is the central angle on the same arc AB, and relation between these two angles we have to prove here. And relation is what? Angle AOB is twice of ACB, that we have to prove here, is it? So let's start by providing here given, is it? So in the given, in the circle with center O, in the circle with center O, so here in the circle center O, okay, angle AOB, is it? So this is the central angle. Angle AOB is central angle, and angle ACB is inscribed angle standing on same arc, AB. That's the thing which we are given here, and let's write what we have to prove, right? So to prove is this angle, central angle AOB, is twice of inscribed angle ACB, that we have to prove here, is it? And for this we have to go through construction, right? And that what we do here is CO, is it? The CO radius we draw or we join and produce this line towards the arc AB, right? Okay, so we write here okay, let's make it first, is it? So C and O is joined and produce this way, right? So here, okay, so up to end point I go here, right? So to construct, so you say here draw radius CO and produce radius up to point N, is it? You may intercept AB, or you may keep it within the arc AB. So, and after doing that, now we start the proof. So in the proof over here, okay, so let's write here statement and reasons. Statement and reasons. So what we do here in this is, so we take help of two isosceles triangles, AOC and BOC, right? So in AOC triangle, why I'm saying isosceles, because AO and OC, these both are radii of the same circle and they're equal, is it? That is why this triangle AOC is isosceles triangle, and same like COB is also isosceles triangle, because there is CO and OB are equal, is it? And the thing is what, if the triangle is isosceles, then their base angles we can say equal. So for triangle AOC, their base angles are these two, is it? I'll mark here. Okay, so angle A, is it? This angle and this angle, which are OAC and ACO, they are the base angles of this isosceles triangle. So these two you can say equal. And furthermore, so with the same concept, is it, in another triangle COB, this angle OCB and angle OBC, is it, then you can say equal, since they are base angles of the isosceles triangle COB, is it? So that is say first here. So in the proof we go with the number first. I'll make here a line on it. So in first one, in triangle ACO, right? So we say here angle OAC, is it? Angle OAC equal to angle ACO, is it? So reason is base angles of isosceles triangle. Base angles of isosceles triangle being OA equal to OC, since O and OC both are the radii of same circle, is it? And very same alike we can go in triangle COB, and we can say angle OCB equal to angle OBC, is it? So this is very same as number one, as statement number one being OB equal to OC, because they are radii of the same circle, is it? And now next thing what we do here is, like, now there exists theorem in triangle with the relation of the exterior angle and its opposite interior angles, and that's what exterior angle of the triangle, right? So that equals with the sum of opposite interior angles. So I show with one rough diagram over here down. So this is the exterior angle, is it? And its opposite interior angles are these two, this one and this one, is it? So this exterior angle which we have drawn, that we can say equal with sum of these two interior angles, right? So same thing happens over here. ACO and N when we see, so here angle AON is the exterior angle, is it? So angle AON, this is the exterior angle, and its opposite interior angles are OAC and ACO, is it? So we can say here AON is equal with the sum of OAC plus angle ACO, is it? So we provide reason what, exterior angle equals with sum of opposite interior angles, is it? So we provide the reason. This area is here. So reason is what, exterior angle equals with sum of its opposite interior angles. And now this is going to give you what OAC and ACO you have made equal, is it? So in place of OAC you can keep your ACO. So in number 4 you can get here AON equal to twice of, okay, I won't go directly. So first I keep here in place of OAC ACO, let's keep, is it? ACO plus ACO will become, is it? OAC I have replaced with ACO, and that will give you twice angle ACO. So this I got from 1 and 3, is it? So in number 4 we say here from 1 and 3, is it? And I'm number 5, is it? After getting AON twice of ACO, now go with the angle BON. Angle BON. So let's draw the related diagram here in raw. So here CO N and B, is it? So here NOB or BON, this is the exterior angle, and its opposite interior angles are these two, is it? OCB and OBC. So what we can say here is BON is sum of the opposite interior angles OCB and OBC, is it? So BON we can write here sum of the angle OCB plus angle OBC, is it? So reason is very same, is it? So reason is as number 3, exterior angle equals with the sum of opposite interior angles, is it? So you say here as number 3, is it? And once we do that, now angle BON, is it, which is sum of OCB and OBC. Now that OBC you can replace with OCB, is it? So OCB we keep same, and OBC we get replaced with OCB, is it? So this will get you 2 times of angle OCB, is it? So this we got from number 2 and the 5, is it? So from number 2 and 5. And once you get that, now these two, number 4 and 5, let's get added, right? Okay, so in number 7, is it? So 4 and 6, let's get added. So 4 you do have your AON BON, angle AON plus angle BON. On left side I have added, right? And now on the right, is it? So left we have added AON BON, and on the right we do have here 2 times AOC ACO and 2 times of OCB. So those two let's get added. So 2 times angle ACO plus 2 times of angle OCB. So these two we getting added, is it? So here in number 7 we give the reason equal addition from 4 and 6, is it? So we say here equal addition from 4 and 6, equal addition from 4 and 6, is it? And now this is going to give you what, see, AON and BON when you get added, these two, is it? So I show this here roughly first. AON, is it? AON and BON. So these two if we add, you get the whole angle AOB, is it? So that you have to use here. So in the sum of AON BON, is it, we can say here angle AOB, is it? And 2 will be taken common, so there will be ACO plus angle OCB, is it? And the thing is what ACO plus OCB, what you can get there from, is it? So I show this here in the rough, right? So angle ACO, is it? ACO is this one, ACO, is it? And angle OCB, OCB is this one, is it? OCB. So if we add these two angles ACO and OCB, you're going to get their whole angle ACB, is it? So you can write here in the sum of these two angles ACB, is it? So twice of angle ACB you can write, is it? And for this you give the reason whole partition. If portions you add, is it, or parts you add into the whole, then you give the reason what? Whole part section. By sorry, by whole parts section. So this way we got here angle AOB is twice with the angle of ACB, which is central angle is double of inscribed angle standing on the same arc, that we got proved. So we say here this is proved. That's it. So this was the first theorem of the circle topic from the grade 10 geometry, circle mathematics. So like now I will go with the another theorem of this. And now second theorem will be based on the same first theorem, right? And that will be the relation between the two inscribed angles standing on the same arc. So before starting on that, let's make this clear. Okay, so I made this clear, is it? And now I'm going with the second theorem, is it? So in the second theorem, so what's there? Let's see. Prove that now inscribed angles, right? Prove that inscribed angles standing on same arc, inscribed angles standing on the same arc are equal. Okay, so this we have to prove in the second theorem, and for proving of it we will be taking help of the first theorem which we just proved before, right? So for this we first make the drawing of the one circle. Okay, so one circle I draw here, and now after drawing the circle, let's make here two inscribed angles standing on the same arc, right? So okay, I take arc from here to here, right? And I put center O, right? Now let's make the central angles. Now first inscribed angles, right? Okay, so one inscribed angle I draw this. Okay, so arc I have taken AB. On this arc I'm making inscribed angle ACB, first one, and next inscribed angle let's make. Okay, I'm keeping it this side. So another inscribed angle I'm making here, this one, I give name here ADB. So we see here two inscribed angles which are made on the same arc AB, right? ACB and angle ADB, is it? And these two inscribed angles will be equal, that we have to prove here, is it? So let's start by providing here given first. Okay, so first we provide a given, is it? So in the given inscribed angles ACB and ADB, these are standing on same arc, AB, is it? That's the thing which we are given here. You may say in the circle with center O, in the circle with center O, is it? And after that what we have to prove, that we write here. So to prove is these inscribed angles ACB and angle ADB, these are equal, that we have to prove, is it? And for proving of it So how we start is we do here one construction, is it? So right to construct. So as a construction we draw here two radii, like so one radius is OA, okay, and another radius is there, another radius is BO, is it? So we drawing here these two radii, right? And this is construction, is it? So I'm making this the dot mark, right? Okay, so construction is done, is it? Draw radii, OA and OB. So these two radii we have drawn here as the construction. And now in the proof we go with statement and reasons. Let's make your box. Okay, so construction is done. Now statement and proof. The first one, right here, AOB, that is a central angle which is standing on the arc AB, and on same arc AB we see here inscribed angle ACB, is it? So what you can say here is AOB is twice of angle ACB. So reason we provide here, central angle is double of inscribed angle on the same arc, is it? So central angle is double of inscribed angle standing on same arc. So same arc is AB, on which angle AOB is the central angle and angle ACB is the inscribed angle. And now with the same rule, is it, or with the same method, let's see here another inscribed angle, is it? So on the arc AB, is it, on the arc AB you see here you see this inscribed angle, which one is next is ADB, is it? So angle ADB is the inscribed angle which is made on the same arc, is it? Angle ADB, and on the same arc AB central angle already standing. So we can relate these two angles AOB and ADB with the same reason, is it? So what you say here, angle AOB, is it? AOB, which is the central angle, and angle ADB is the inscribed angle which is made on the same arc AB. So you can say here angle AOB is twice of angle ADB, and reason will be provided same, is it? So as one you can say central angle is double of inscribed angle on the same arc. And now in the number 3, so these both angle twice ACB and twice ADB, they are being equal with same angle AOB, is it? Twice ACB equal with AOB and twice ADB is also equal with AOB. So twice ACB and twice ADB you can say equal, is it? So in number 3 you can say here twice ACB is equal with twice angle of ADB, is it? And once you say that, reason we provide from 1 and 2. So from 1 and 2, is it? And after that on either side 2 will get cancelled, so this will give you angle ACB equal to angle ADB proved, is it? So say from number 3, so proved, is it? So done, is it? So this is the second theorem of the circle operator geometry. Now I go with the another theorem from this. So let's make this clear first. Now I go with the another theorem, is it? So there another theorem is relation of the inscribed angles of the cyclic quadrilateral. Okay, so here I say prove that opposite angles of cyclic quadrilateral are supplementary. So this is the another theorem concerning with the inscribed angles, which are of the opposite inscribed angles of the cyclic quadrilateral. And before understanding this, you have to understand the cyclic quadrilateral. So let's understand that first, right? Okay, so one circle I have made, is it? And now cyclic quadrilateral is that one which is formed by joining any 4 points of the circumference, right? So I'm keeping this way, see, A, B, is it, and then C and D. So these are the 4 points, any 4 points which I have taken from the circumference of the circle. So if I join these 4 points, is it, to form any quadrilateral, that quadrilateral is called cyclic quadrilateral. So let's join here. So AI join with B, is it, then BI join with C, then again CI join with D, and finally AI join with D. This way, here which quadrilateral has been formed, this is the cyclic quadrilateral, and its opposite angles are here, which you see, these are A with C, is it, and another B with D, is it, angle B with D. So these pair of angles, right, are supplementary, that we have to prove here. Or supplementary means their sum will be 180 degree, that we have to prove here. So I'm going with only one pair, right? Okay, so let's go with first providing given, is it? So here in the circle with center O, ABCD is a cyclic quadrilateral. So I start with given here. In the circle with center O, ABCD is a cyclic quadrilateral. So that's the thing first what is provided us, is it? And we have to prove here its opposite angles are supplementary or their sum is 180 degrees. So one pair I'm taking, so one pair I take here with B and D, right? So let's provide here sum of angle B and D is 180 degrees. So B is here angle ABC and D is angle over here ADC, is it? So their sum equal to 180 degree we have to prove here, is it? And for proving of it we need to go through one construction, is it? So we say here to construct. So as a construct what we do here is it, so for B and D to make supplementary, is it, so we draw here radii OA and OC, is it? So let's draw here radii OA and OC. So OA I get joined, is it, and then OCA I get joined, right? So two radii I have drawn, right? And now after drawing these two radii, right, okay, so let's say here first draw radii, draw radii OA and OC, is it? So two radii we have drawn, and once after we draw these two radii, right, so let's understand the concept of the central angle and its angle standing on the same arc, right? So here you see angle B, is it, angle B we see here this standing on the arc, this one, is it, ADC, is it. So what you can say here is it, on this ADC arc, angle ABC is the inscribed angle, and then central angle is there, this one, AOC, is it. So you can relate AOC and ABC as the central angle and inscribed angle standing on the ADC arc. And what you can say here, angle AOC is twice of angle ABC, is it, first thing. And now if we see the same concept, if we talk about the same concept through another arc, right? So if we see this through the arc ABC, right? So on this arc, central angle is this one, right? So its name is also AOC, but it's greater than 180 degree, is it. So this angle we have to say reflects central angle AOC, and on the same arc ABC, inscribed angle you see here, this one, ADC, is it. So these two angles, reflects central angle AOC and inscribed angle ADC, they are standing on the same arc ABC. That's why they are related. And we can say here reflex angle AOC is twice of angle ADC, is it. So with use of this relation of the central angle and inscribed angle, we'll be proving this theorem. Alright, so let's go for it. So I'll make this clear. Okay, so we write here proof and then statement and reasons, is it. So first we go with the central angle made on the arc ADC, is it. So on the arc ADC, central angle you see there AOC, is it. So angle AOC is twice of AOC central angle made on ADC arc, and on the same ADC arc there is angle ABC, is it. So AOC is twice of angle ABC, you can say, first one. And second one, now I take from the arc. Okay, first give the reason of this. AOC twice of ABC we did by taking from the arc ADC. So in the reason we say here, central angle is double of inscribed angle. Central angle is double of inscribed angle. Standing on same arc, and arc name is the ADC, is it. And now second we go, and in the second, now we're taking from the arc ABC, which I have made with yellow color. So on that arc ABC, central angle is AOC, but it's reflex, which is greater than 180, is it. So we say here reflex angle AOC is twice of, is it. So on the arc ABC, which I made with the yellow color, right, on that arc inscribed angle is ADC, is it. So reflex angle AOC is twice of angle ADC, we should say, is it. So reason we provide same, central angle is double of inscribed angle. Now I just write here standing on same arc ABC, is it. Same relation, but standing on the same arc ABC. And after writing that, now we'll be adding these two, right. Let's make a line once. Okay, so let's get these two added, is it. Angle AOC plus angle reflex angle AOC, is it. So these two I have added. So on left I added, and on the right also I'm adding. So twice angle ABC plus twice angle ADC, is it. So we provide here reason equal addition, make zoom, equal addition from 1 and 2. 1 and 2 we have added, is it. And number 4, so AOC and reflex AOC, is it. So two angles if we add, okay, see, I saw it in rough. Alright, so AOC and reflex AOC, is it AOC and reflex AOC? If we these two get added, alright, so whole 360 degree will be formed, is it? So in place of the sum of these two angles, we can write here 360 degree, is it? And here 2 will be taken common on the right side, so twice 2 taken common, angle ABC plus ADC remains there, is it? And number 4, and reason we provide here, complete turn measures 360 degree. Complete turn measures 360 degree. And now this 360 degree will get divided by 2, and you get there 180 degree. So we get there ABC plus angle ADC equal to 180 degree is from 4, is it? So we got here the opposite angles, sum of opposite angles of cyclic quadrilateral, which are here ABC and ADC. Their sum we got equal to 180 degree, hence it's proved. Now few remaining theorems are there, right? So that those theorems I'll be making later time in another video. Up to here you have watched, and I hope you have understood these 3 theorems. Thank you for watching, everyone.